Hi all. I'll be uploading solution of problems that involve momentum conservation and collisions in a continuation to what we did in class uh, this week on Monday. So review these problems and try to do some others that are available in the book. Okay, so let's go for it. So let's start with the number 10. Number 10, 10th edition. A man claims he can safely hold on to a 12 kilograms child in a heads-on collision with a relative speed of 120 miles per hour that lasts for zero point 0.1 second. So the kid has no seat belts, and the man claims he can hold the child that way. So find the magnitude of the average force needed to hold on the child. Okay, this is the problem. Okay, so let's first thing to do in a type of problem like that is to try to visualize the situation. So I like to do a little sketch of things. So we have a kind of a horizontal line, and so let's make a child here, right? And the child has a mass of 12 kilograms, 12 kilograms, and this child is moving with the speed, and I will write not the speed but the velocity vector associated with this child. So I'm giving a direction, right? So I'm giving a direction, so the child is moving that way, and the velocity is 120 miles per hour. Oh God, it's getting a ticket. And and somebody claims that if there is a head-on collision that lasts zero point 0.1 second. So somebody claims, the father or the mentor, whatever, claims that it can hold the child that has 12 kilograms that's moving with 120 miles per hour on a heads-on collision that lasts zero point 0.1 second. So let's see if this is even feasible. So the concept we are going to use here is the concept of impulse. Remember that one? So impulse is a vector, and impulse is given by the product between force and the amount of time that force is taken care of. So certainly, as we discussed in class, usually when these collisions take place, the force that is being responsible for the stopping process, the force is not uniform. The force change in time. But what we do, we'd say, hey, there is some average force during a certain average time interval that is equivalent to the total load of the real force that happened over probably a slightly longer time interval. So we can always say, at least in at the level we learn this stuff in physics 2A, that F del T is the impulse. But also we found as this force applied in attempted to change the state of motion of your studied object, this is equal also to the change in momentum. And change in momentum is the product of mass times the change in velocity. Okay? So in this case, you have the means to relate force, and that is what you want to solve for. The time is given, and we have to play around with this. Well, the mass I have, 12 kilograms, I have the initial velocity of 120 miles per hour, and the final velocity is I want to stop the child, 0 meters per second, right? That's when the child stops. So in these problems involving collision, momentum, conservation of momentum and all, you have to be careful with orientation. So, and as a matter of practice, I always call the positive orientation the one to the right. So orientation positive to the right, which means your initial velocity is a positive number. Okay. So, but see, we are using international system units, metric, m for meters, time for seconds, and I have a speed given in miles per hour, so I have to convert that to meters per second. This is important. So let's work on that. So the speed of 120 miles per hour, 1 mile is equal to 1609 meters, and 1 hour is equal to this many seconds. Okay, so what I do, I just replace it in the equation. And then I have my velocity or speed in meters per second. So 120 times 1609 divided by 3600 meters per second. And then we have our speed converted into 53.6 meters per second. So now I can go back to my basic equation. F del t is given 0.1 seconds is equal to the change in momentum, which is 12 kilograms, and multiply final velocity. Be careful here. You have to follow this definition when delta is given in physics equation is always telling you the differential or the subtraction of final quantity minus initial quantity, and you have to pay attention to that. So the final quantity, the final velocity is 0. The initial velocity is 53.6 meters per second. So that force is going to be 0 minus that. It's a negative value. 12 times 53.6 divided by 0.1 newtons. So the force is equal to, bring my calculator here, 6432 negative 6432 newtons. So force is a vector, and this negative sign right here, this negative sign is telling you the force that is being applied on the boy, the child, is a force that goes on the opposite direction. And the magnitude of this force is equal to over 6,400 newtons. Now, can a person do that? Can a person be able to do that? So just a matter of comparison. Let's say you know me, right? So my mass is about 80 kilograms, 70 kilograms in a good days. So my weight is 80 times, let's make G 10 meters per square second. Okay, so what is my weight in newtons? 800 newtons. So 64 newtons and 800 newtons means when the accidents happen in 0.1 seconds, the man is claiming that he can hold the child probably with one arm because he or she will be driving with the other arm with a force that is 8 times my weight, as if that person were holding 8 people like me with one arm. Is that possible? Forget about. No way. Let's take a look at this problem number 11. Problem number 11. You have a ball of mass given 0.15 kilograms that dropped from rest from a given height. So keep thinking, keep drawing the problem in your brain, in your mind, because that's how I start the problem. I do a little sketch on it of it. It rebounds from the floor to reach a height of 0.96 meters. What impulse was given to the ball by the floor? Which impulse was given to the ball by the floor? So we want to solve for impulse. So what do we do? First of all, we try to visualize the situation. So we have a floor and we have a ball that is being dropped from, by the way, the ball has a mass. Mass is given. And is dropped from rest. So the initial speed, or the initial velocity in this case, is 0 meters per second, because that is how it's being dropped. And the height from which the ball is dropped is 1.25 meters. 1.25 meters. And here's the ball. So the ball comes down, hits the floor, and then for some fractions of a second, it rebounds and goes back, but not to the same original height on 0.25 meters. I think you all have that as part of your experience, right? When you kick a ball on the floor, the ball never goes back to the same height because some loss happened when the ball goes in collision with the floor. So we want to solve for impulse, and impulse we saw is a vector that is given by the force as being applied on the studied object, in this case a ball, during a certain time interval, and that is equal also to the change in momentum of the ball. Okay, and change in momentum, it's always good to write this all the time because it helps to fix concepts. Is the final velocity minus initial velocity multiplied by the mass of that object. Okay, okay, so as we do with all problems involving momentum and impulse and forces, we have to set our orientation. So most of the, in fact, all the motion is occurring in a vertical line, meaning I'm going to set my positive axis, my y-axis, facing upward. So all vectors that happen to be pointing upward, they will receive a positive sign. And vectors that are pointing downward, they will receive a negative sign. Okay. So we want to solve for impulse. What do I have? I have mass, I have initial velocity, and I have the heights. I have the height. Well, when you look at the equations that involve impulse, you know you have to either use this or that. That will give an impulse. You don't have the force. By the way, the force that is acting on the ball when collision takes place is the normal force, right? At that moment is a variable normal force. And we know to begin with, the sign of our calculated force must be positive. Why? Because it's pointing upward, right? We have to, because otherwise the ball would keep going through the floor. So, but we don't know the force. If we calculate a force, we would get a positive sign, but we don't have the force. We don't have the time the collision takes place, so we cannot use this equation here. And look at momentum. Momentum, I have the mass, so that's good, but I don't have the velocities right before the ball strike the floor, nor the velocity the ball has right after it leaves the floor. I don't have that. I don't have VF, and I don't have V initial, because the final and initial are not the velocities at this point, but the velocities were that precedes and follows the interaction of the ball with the floor. I don't have those. So what do? I calculate them. And how do I calculate them? Well, I have to use what I learned in chapter 3 or 4. I can also use conservation of energy. Since conservation of energy in our next exam, so let's use that one. So I have a point A, an initial point, where the ball is dropped, and I have my lower level, point B. So when I use conservation of energy to solve for unknowns, what I do, I set position A, position B, and then I go down to the list of energies I have available in this process. So do I have kinetic energy at point A? No, I don't, because the ball is dropped from rest. So I don't have kinetic energy. Do I have kinetic energy at point B? Yes, I do. Is when the ball is about to strike the floor. And that is what I'm calling here, the initial velocity, the velocity that is about to strike the floor. I should have changed this symbol here. I should call this V naught, H naught. Okay, very good. Now, how about gravitational potential energy, which is the other energy involved? Do I have gravitational potential energy at point A? Yes, I do. And that is given by mgh. Mg times the vertical displacement of your object, of your system. And so it's mg del y. And I'm gonna put um, a y just to emphasize that I wanted this to be in the vertical direction only. And a point B, which is my ground level, gravitational potential energy is 0. So those are the only two energies I have in this type of problem, because I don't have springs, I don't have tensions doing work, I don't have frictions, that's it. So then I go and I replace all of that by numbers. So energy at A which is mass times g times the displacement, which is 1.25, is equal to half mass times v initial, that I'm calling square. So then I can solve, I mean, the mass can be simplified, and then I can find my initial velocity using conservation of energy, and that's going to be, that is 4.9, oops, 4.9 meters per second. Okay. So how do I find the final velocity, which means the velocity the ball has right after collide with the floor? Well, I use also conservation of energy. I can extend to another column here and call this point C, point C. And then ask the same question, what is the energy I have at C? Do I have kinetic energy at point C? No, because the ball stops. Do I have gravitational potential energy at point C? Oh yes, I do. Is mg and the vertical displacement at C, right? So 0 is 0 and mgh is 1.5 or 0.15 kilograms times 9.8 meters per second. That's the acceleration. Gravity times the height, 0.96. Well, but I want to find um, what originates the rising of the ball. So I could use B, but I mean, I already found the initial velocity before collision. So I want to compare C, the condition of energy in C, with the moment the ball just finished colliding with the floor. And I'm going to call that configuration D. So what is the kinetic energy at point D? Well, is the velocity is given by half m times the velocity in which the ball leaves the floor, Vf squared. And the gravitational potential energy is 0. See? So what I do next, and I'm going to use this little corner here. So half m vd squared is equal to mgyc. My m cancels out, so vd is going to be equal to 2 times 9.8 meters per square second times yc, which is 0.96 meters. And then vd is equal to, then we go to our calculator, 2 times 9.8 times 0.96 equal, and then I take the square root of that, 4.34. Okay, what is the sign of this velocity? Well, the sign of this velocity is a positive sign because it's going upward, right? So the initial velocity here, the velocity in which this ball rises up, is positive. But the initial velocity, if I put a vector sign like this, I put a vector sign like that, the initial velocity is a negative sign. Why? Because it's about to strike the floor. The path is downward. The velocity is negative. Therefore, my impulse is going to be equal to the mass times the final velocity, which is a positive 4.3 meters per second in the j hat direction, minus the initial velocity, which is also turned out to give me a positive number. And then what I do next, I sum, because negative with negative gives a positive resulting sign. I add these two quantities multiplied by 1.5, I have the impulse. I could possibly determine the force that is responsible for this shooting up if I knew the colliding time. Okay, but this is not asked in the problem. So let's try now give a closer look to collision in case you have two objects colliding, but at the same time collision takes place, they move, both of them. So the two examples, and most of the examples I did in class, the collision was taking place, there was impulse happening, there was conservation of the change in momentum was happening, and we were applying that to figure out the impulse. But in those examples, one of the participants colliding objects was not moving. The floor is not moving when it collides with the ball. The ball is not moving when collision takes place, right? So so let's take a look at example number 27. We have a 65 kilograms person, and this person throws a ball, a snowball, forward with a ground speed of 30 meters per second. So ground speed means the velocity of the ball with respect to the ground is 30 meters per second, right? So a second person with a mass 60 kilograms catches the snowball. Both people are on skates. And I think, yeah, so down here it said disregard frictions between the skates and the ice. So the first person is initially moving with the velocity 2.5 meters per second. The second person is not moving. What are the velocities of the two people after the snowball is exchanged? Okay, so let's work on that. And as always, I like to start with a little sketch. And here is somebody that's carrying a snowball. This is a snowball. And both of them, the person and the ball, are moving to the right with a certain speed. Okay, and I think the problem tells us which one it is. Let me see. The first person is initially moving forward with a speed of 2.5 meters per second. Okay, so both of them move 2.5 meters per second, and I hat means I'm going to call all directions to the right my positive direction. Okay, so just to keep a reference. So when the person moves to the right with the 2.5 meters per second velocity, it means the snowball itself has also the same velocity. Like if you are in a car, the car moves 60 miles per hour. Tell me what's your speed. Speed is also 60 miles per hour because you are inside the car, correct? Okay, so what happened? There is a phenomenon we call collision or explosion, physically speaking, that now the two are separated. The person is to move with a velocity I'm going to call final, which I don't know which one it is, and I have a snowball that is moving towards somebody else, which is right here, that is moving towards somebody else with a speed that is 30 meters per second. Okay, so this is 30 meters per second, and is a positive because it goes to the right. Okay, and the velocity of this person, in fact, this is velocity of, sorry, I think I'm making a confusion here. This is the VF is the velocity of the person, and velocity of the snowball is the positive 30 meters per second. Okay, so since there is no friction, since the net external force acting on both of them cancels out, we can say conservation of momentum exists when the snowball is thrown away. So we can say before collision, if I could determine the total momentum that happened before collision, that is going to be the total momentum after collision. So before momentum, what do I got? Well, I get a person that has a mass of 65, I think, 65 kilograms, right? Let me write directly there. So the person has a mass of 65 kilograms and moves with an initial velocity. Do I have that? I think I do. Moves forward with a velocity of 2.5 meters per second times 2.5 meters per second to the right. But I also have a snowball that has a mass, so I'm going to put plasma here, 0.045 kilograms, that has the same velocity, 2.5 meters per second. And see, I'm putting a positive sign in the velocity because they all go to the right. Okay, so I'm obeying, I'm translating, I'm repeating the sign in both equations. This is before. Now I have all the quantities, so I could calculate that, right? And I'm gonna do that right away. So 65 times 2.5 plus 0.045 times 2.5. So 162.6. So this is equal 162.6 kilograms meters per second. So that is the total momentum of the system, person, and snowball before that person throw the snowball away. Now, after these, what we call collision takes place, what do I got? Well, I have this 65 kilograms person moving with a velocity that I want to find what it is. I don't know what that is. I'm going to call VP for velocity of the person after, plus the momentum of the snowball. The snowball is still moving, right? And that is 0.045, which is the mass of the snowball, kilograms, times the velocity it has, and that is given the velocity with respect to the ground. And I'm putting a positive sign because the velocity is positive. It was the snowball was thrown in the direction I'm calling positive. Okay, so I can calculate some of that. So I'm bringing my calculator here. So 0.045 times 30, and I get 1.35. So essentially, this is the same. This is the same as 65 kilograms velocity of the person after plus plus 1.35 kilograms meters per second. So see how nice it is. I have my I have a number, and I have an unknown. I can calculate, I can solve for the velocity of the person after collision, and then I will find the velocity of the person after collision is equal to 162.6 minus 1.35, and I will shoot the unities to the right hand side here just to make my life easier, divided by 65 kilogram, and then my velocity shall be 162.5 minus 5 divided by 65, 2.48 meters per second. So that's the velocity of the person. So see, the initial velocity of this person, by the way, is a positive number, which means if I want to give a vector symbol to it, I have to pay attention to this positive sign. So see, the initial velocity of that person is 2.5 meters per second. After that person throws the snowball, the velocity is slightly less, 2.48. It's not 2.5. It loses some time, right? Right? So we can say the momentum that was the momentum was taken out once the snowball left that person. Now, the snowball, let's go to the second part of the problem. The snowball goes and finds this person that is originally was not moving. And then we can, I can bring a hard eraser and do all over again. So now, I think I erased it and I forgot. So the velocity of the snowball, the velocity of the person is 2.45, right, meters per second. Okay, so this person here, which has a mass of 60 kilograms, is that correct? 60 kilograms, yeah. This person has a mass of 60 kilograms and initially is not moving. And this person holds the ball after collision takes place. So we go to a third stage in our problem when collision again takes place and this person is moving in, I will assume, I might be wrong, but I think after this person collects the ball, it's going to be moving to the right. So I'm gonna write as a symbol velocity of the person after collision takes place. So what we have before I have a ball that has a mass of 0.045 kilograms moving with a speed of 30 meters per second. That's the momentum before, plus a person that has a mass of 60 kilograms, but its velocity is 0. This is the total momentum before. So when I punch that in my calculator, the total momentum before the system, which is 0.045 times 30, 1.35 kilograms meters per second. After collisions take place, that person is holding the ball, right? So which means both of them now have the same velocity. So is the mass of person 1 plus the mass of the snowball, remember they are together now, times the final velocity of the person after they get together. This is a totally inelastic collision, right? So they glue, they get together. And so energy is not conserved in this case. And then we can find, when we make this quantity here, when we make this number equal to that number, we can find our velocity after, and that is going to be 1.35 kilograms meters per second divided by 60.045 kilograms, and that give us the velocity of that second person, that is going to be equal to 2.022 meters per second, or in other words, this is pretty much 2.2 centimeters per second. It's a very small speed, you barely can see that, but assume there is no friction in there, that's going to be the resulting action. The last problem I would like to have you guys working is one that involves not only conservation of momentum, but has two segments. Is one that is you have two parts of the problem. The first part, you have a collision taking place, and in the second part, we have you can use conservation of energy to solve. Okay, so let's take a look at problem number 39. So problem number 39 goes in the following way. You have a bullet with a mass 0.30 kilograms that is fired vertically with a speed of 200 meters per second into a baseball. So there is a baseball, the mass is given 0.15 kilograms, that is initially at rest. How high does the combined bullet and baseball rise after the collision? Assume the bullet embedded itself in the ball. Okay, so let's try to understand this problem. That's problem number 39. Problem 39. So let's assume we have a basketball or a baseball that is initially at rest, and a bullet that is moving vertically with a velocity in the vertical direction and the upward direction 200 meters per second, and this bullet has a mass of 0.0330 meters kilograms, and this basketball where the bullet is going to be embedded has a mass of 0.15 kilograms, right? And it's not moving. It's not moving. So as always happens in this type of problem, I'm going to make my positive orientation upward. So collision is going to take place. And what's going to happen? Well, my system, basketball, and embedded bullet will rise up from here to there, height h, right? You see that? So just to visualize better the problem, take this away so you can see the problem better. So here's the base level of the problem when the bullet is stored embedded in this big ball. Okay. So when the collision takes place, what happened? Well, I have a bullet that has a certain velocity, that once it embeds or embedding in this ball, the ball in its turn start moving up with the velocity that I'm called after, with a velocity that eventually, and because it's moving upward, eventually it stops, right? Eventually stops. So this velocity I'm calling after is the velocity system ball and bullet right after the embedding took place. So perhaps this embedding took place in fractions of seconds, I don't know. But the point is, both of them start moving up with a certain velocity, which I'm calling v after. So for this moment of interaction between bullet and ball, when the ball starts launching itself upward with velocity v after, I can say, well, the total forces at play in the system are internal. So I can say, okay, there is conservation of linear momentum. Okay. So before collision, what do I got? I got the mass of the bullet times velocity of the bullet plus mass of the ball times velocity of the ball. And I know the ball was not moving. This is zero. So before collision, the only momentum I have is the bullet itself, 0.03 kilograms times its velocity, 200 meters per second. So that's going to be 6 kilograms meters per second. Okay. So after collision took place, what do I got? Well, I have now the bullet embedded in the basketball. All of them, both of them, moving afterward with the v, which I'm calling after. So if I put numbers in it, mass of the bullet, 0.03 kilograms, plus mass of the basketball, 0.15 kilograms, the after, I can write 0.18 kilograms V after and calculate my V after, because momentum before collision can be make equal momentum after collision. So velocity after collision is going to be equal to 6 kilograms meters per second divided by 0.18 kilograms, and that is equal to 33. Okay, and the positive is telling me that velocity is upward. Okay, so now I have my velocity after, and then I can go on to calculate the height using conservation of energy. I have position A, position B, and I do my little energy diagram, A and B, and then I go down the list of energy availables. Which energy I have in A? Do I have kinetic energy? Yes, I do, given by half mass of the bullet plus mass of the ball times its velocity square, 33 square. Do I have gravitational potential energy? No, I'm calling that my ground level. So at point B, do I have kinetic energy at point B? No, but I have gravitational potential energy given by m g. I'm sorry. I don't have too many numbers here. M times g times vertical displacement h, which I want to find. So mass can be canceled out, and then the height, when you make those two quantities equal to each other, then we find the height is given by 33 square divided by 2 times g meters. Okay, and then you plug that in your calculator, and then you get it done. Good enough? So in this problem, there is no conservation of energy. It's a total inelastic collision where energy is lost when the embedding takes place. So let's do our last problem in which we might have conservation of energy in the mix. So elastic collision, so all this, the previous problem was one in which energy was not being conserved. The energy was conserved when the two embedded objects move upward. So we have total mechanical energy close to the floor is equal to total mechanical energy on the top. But during collision, when the collision was taking place, and collision, remember, takes a very short amount of time, when collision took place, energy was not conserved. There was no conservation of energy. Now, this is not true in types of collision we call elastic collision. So let's go back to, I think at the end of the chapters, you have some. Okay, right here. In elastic collision, you do have, as long as external forces are cancel out, the only major forces playing any role in the collision are internal. So conservation of momentum, as we have been studying, can be applied. So you use as we have been using till now. Now, in addition to that, you also have conservation of kinetic energy. So the total kinetic energy of your system before collision takes place equals the total kinetic energy after collision takes place. And you see, this is mass of the first object, the initial velocity of the first object, plus the half mass of the second object and its speed square initial. It's equal to half of the mass of first object, velocity of first object after collision square, because they separate, plus half of the second object times its speed square. So those two quantities are the same, but you can do some simplification, and 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 you and let me show you how that simplification takes place. So if you have half m1 v1 before square plus half m2 v of the two object before square, the kinetic energy total of the system is equal to the kinetic energy after total adding up of the first and second object square. So this is true. So what you do a little bit of I mean, first you can get rid of this 1, 2 everywhere, but what you can do, you can take v1 m1, and then you can do v1 before square subtract from v1 after square. So what I did, I took this term and I moved to the left hand side, and as I do, it switched the sign. And on the right hand side, I have my m2 v2, I put a negative here, negative m2. I'm going to take this guy and move to this side, v2 before square minus v2 after square. So these terms can be simplified or factored like this. that multiply. So I don't want to lose you guys right now, but if you now take a ratio of M2 and M1 from conservation of momentum, because conservation of momentum, you have these, right? Before M1, V1 after. This is conservation of linear momentum. So if you do the same thing, you subtract, bring this to the other side, and move this around, and blend this equation. I'm kind of regretting I did that, but anyways, you can um, you can wrong one. You can get this nice equation here, and let me write in a piece of paper so I can call it sometime later. V1 initial, or V1 before, minus V2 before is equal to the negative of V1 after minus V2 after. Okay? So it's a handy-dandy equation, prevents us from using second-degree equations and try to, or quadratic equations, and it simplifies a lot our lives. So if you have in your problem sets or in your homework or in your exams, you have elastic collision, what I recommend you to do is always using your conservation of linear momentum equation, which is have been done so far, and this other handy-dandy equation. So let's see if I can find a problem so we can try to solve it. Take a look at problem number 45. The problem number 45 is one in which you have a billiard ball that rolls across the table and approach. What? Wait a second. What is my problem? No, problem number 45 is one that you have a 25 grams object that is moving to the right with a velocity 20 centimeters per second and overtakes and collides elastically. This is the key the person who wrote the problem is giving us, indicating there is conservation of kinetic energy in the system with an identical ball. So the identical ball means the mass is the same. Find the speed of each ball after collision. Okay. Part A, and that's the only one I would do, when the second ball is at rest. Second ball at rest. So the masses are the same because the balls are identical, right? So let's try to do that one. So there you go. So you have a table, have a ball, have another ball. This second ball is initially at rest, so I'm going to set my positive direction to the right, and they collide, and after collision takes place, I don't know, but I don't know their velocity, right? Velocity 1 after, velocity of the two balls after. This is the velocity of So what do I know? It is given to me the ball has a mass of 25 grams. Here it doesn't matter. You could keep grams and centimeters, but just to keep it consistent with what we have been doing so far, I'm going to convert that to kilogram. This is mass 1, which is also equal to the second mass. The masses are the same, right? 0.0 25 kilograms. And the first ball moves with a velocity v1 before. Make sure you write the symbols correctly, 20 centimeters per second, and that is pretty much 0.20 meters per second. Okay, so I have this and I have that. And I know the collision is elastic. So conservation of momentum allows me to write total momentum before equals total momentum after. So what is the total momentum before? m1 times v1 before plus m2 times velocity before. This is equal m1 times v1 after plus m2 v2 after. See, I don't know the direction of those balls. I don't know if they will carry positive sign or not. So since I don't know, I just leave it that way. And the mass can be simplified. So 0.2 is the first equation I get. 0.2 is equal v1a plus v2a. Okay. Now, my second equation is, well, the collision is elastic, and I have this handy-dandy equation, and that is v1 before minus v2 before is equal to negative of v1 after minus v2 after. And then I just write what I know. v1 before is 0.20 meters per second. v2 before is 0, so I'm not going to write anything, minus v1 after, and then minus applies to this minus becomes positive v2 after. And I have a second relation for v1 and v2. So what I do then, I write this equation. This is equation number 1, this is equation number 2, and then I bring them equation number 2 here, negative v1a plus v2a, and I need to solve for that. The best way to solve the system of two equations and two unknowns in this case is very simple. I just add those two quantities. So 0.2 adding with 0.2 become 0.4 is equal to v1a summing negative v1a gives me 0 plus 2 times v2a, and then I find my v2a is equal 0.2 meters per second, and my v1a, if I put now v2a is equal 0.2, I'm going to find my v1a is equal 0 meters per second, right? So which means this ball comes happily moving to the right with a velocity of 0.2 meters per second, and heads-on collision, elastic collision with this other ball is a dead collision. This v1 stops, and v2 comes out with the velocity the other ball had. Of course, this is not going to be true if the masses are different and the balls are not the same, or if the collision was not perfectly elastic. Okay? Good enough? Okay, so I'm stopping now.